Good evening. My name is Mark Barnico, and I'm the Executive Director of the University of Chicago Francis and Rose Ewan campus in Hong Kong, our premier location in Asia, representing UChicago values of free and open discourse, rigorous debate, and the exchange of ideas. Welcome to the series 1.5 Degrees. We're broadcasting tonight's event live via Zoom, Facebook, and YouTube from the UChicago Ewan campus in Hong Kong. If audience members have questions to submit, you can do so through the questions and answer button by first registering on Zoom. I also encourage you to visit our website at www.uchicago.hk and subscribe to our e-news for the latest news and information. Or you can also follow us on our UChicago Ewan Campus Facebook page. Tonight we continue the 1.5 Degrees Oceans mini-series, which addresses the significant threat of climate change on our oceans. We'll listen to a lecture from Dr. Ann Giblin, Senior Scientist and Interim Director of the University of Chicago Marine Biological Laboratories Ecosystem Center. For those of you unfamiliar, the Ecosystem Center was founded more than 4 decades ago with the mission of investigating the structure and function of ecological systems and their response to changing environmental conditions, and applying that knowledge to the wise management of natural resources. The overall goal at MBL's Ecosystem Center is to lead the effort to bridge microbial to global scales and disciplines to develop the depth of knowledge and new tools necessary to understand and predict the complex behavior of the Earth's natural systems and how they'll change the future. The MBL and the Ecosystem Center leads the convening of very large networks of collaborators from diverse disciplines and from multiple institutions around the world for research at Arctic, coastal, and open ocean sites now at the front lines of global change. Now let's get to the program. And let me first begin by introducing Dr. Giblin. Dr. Ann Giblin is the Senior Scientist and Acting Director of the Ecosystem Center at the Marine Biological Laboratory. She earned her Bachelor of Science in Biology at Rensselaer Polytechnic Institute in Troy, New York, and went on to earn her PhD in Ecology at the Boston University Marine Program in Woods Hole, Massachusetts. Dr. Giblin's research primarily focuses on the cycling of elements such as nitrogen, sulfur, iron, and phosphorus in the environment. The majority of her research is focused around the circulation of these elements in different reduction oxidation conditions in soils and sediments. Another dominant theme in her work is to understand if sediment processes act as a buffer or act to exacerbate pollutants in the environment. For example, much of her work focuses on the nitrogen cycle and the effects ecosystems may have if there are high nutrient inputs from wastewater or fertilizer. Dr. Giblin is deeply involved in 2 ecosystem projects created to study anthropogenic as well as natural environmental change in ecosystems. First, she's the leading PI of the Plum Island Ecosystem Long-Term Ecological Research Site, which is composed of estuaries and watersheds located in northeastern Massachusetts. The goal of this research site is to develop an understanding of the long-term effects sea level rise linked to climate change may have on the watershed. The knowledge gathered through this research site is used in policy and land management with the aim to protect the natural resources of the coastal zone. The second is the Arctic Long-Term Ecological Research Site, located on the north slope of Alaska. There, Dr. Giblin conducted a long-term fertilization experiment in a pair of lakes and observed their recovery to anticipate the effects of what will happen with a longer growing season. Data from this project could inform the management of landscape. Dr. Giblin is a member of the Phi Lambda Epsilon Chemical Honor Society, and in 2001 received an Aldo Leopold Leadership Fellowship. In 2013, she became a Fellow of the American Association for the Advancement of Science. Her research is supported by numerous grants from the National Science Foundation and the USGS. Dr. Giblin, welcome. We're excited to learn more about your work, and I'll turn the floor over to you. And then later I'll rejoin the program to facilitate a conversation and take questions.
Great. Thank you very much for that kind introduction, Mark. I'm going to start right out with some slides. And okay. So I'm going to talk a bit about coastal ecosystems. Given my background and my experience, I'm going to focus largely on salt marshes, but I'll try to end with a little bit of a story about mangroves and how we want to think about coastal ecosystems going forward. Salt marshes are primarily temperate to polar. They ring most of the land masses of the world. But once you get into warm waters, about 16 degrees centigrade, for example, you get mangroves. So those of you that are in the southern part of China, South America, and Africa, your coastal buffer is mangroves, whereas outside of that belt, it's salt marshes. But as we'll see later, maybe this is changing. So as Mark said, I'm going to talk about research in salt marshes. Most of my research is currently done at the Plum Island Ecosystems LTER. That's north of Boston in Massachusetts, if you're familiar with the East Coast of the United States. By our standards, it's a large wetland, although it's only about 60 square kilometers. And it's drained by 3 fairly large upland areas that have various land uses. So we're looking at the influence of land use on these systems, as well as sea level rise. So I'm going to give you a little background on salt marshes. Salt marshes are dominated by grasses. There are 2 dominant grasses, one called cordgrass or Spartina alterniflora, and that's found in the low marsh where the grass is flooded 1 or 2 times a day. And then there's grasses found in the high marsh, primarily Spartina patens. This is salt marsh hay, and it's flooded only about 4 to 8 times per month. Both of these have had a genus name in the last year or so, but I'm going to wait to see if it sticks before I change all my slides. So we have a very distinct zonation of this plant community, and it's over very small elevation differences. So the difference between the low marsh cordgrass and the high marsh might only be a matter of centimeters, 5 to 10 centimeters. So what makes this very strong zonation over this very small elevation gradient? It's because this is a very stressful environment. The sediments are normally waterlogged. There's high salinity, which is stressful for vascular plants. There's very little oxygen in the sediment. Hydrogen sulfide can be in the sediment, and the plants are competing for nutrients. So we have these grasses sort of duking it out in this very narrow elevation zone in this very stressful environment. But the strange thing is, in spite of the fact this is an extremely stressful environment, salt marshes and mangroves are among the most productive ecosystems on the planet. You see here a comparison of a variety of ecosystems, but salt marshes rank right up there with tropical rainforests in terms of their average net primary production. So we have these very productive ecosystems with a very sort of small diversity in the plants. So what happens to all this production? There's no large grazers on the salt marsh. We don't have things like buffalo or elephants. So this salt marsh hay and this salt marsh cordgrass is usually not directly grazed by animals, except it was collected by the early colonists and taken away for cows. But most of what happens to this grass is it dies in place and it starts to be decomposed by microbes. These in turn are eaten by small invertebrate animals like snails and worms. This then ends up supporting a tremendously rich and productive food web. So although microbes are largely at the base, we support rich shell fisheries. The salt marshes and mangroves tend to be very important places for migratory birds, and they're also nursery grounds for shrimp and finfish and other animals. So we have a very rich food web supported by primarily microbes, and in turn by the salt marsh grass. But how do we know that's really what they're eating? I'm just going to do a little slight diversion here to talk about one of the ways we study these kind of food webs. We do this in the salt marsh as well as other places. But if we want to know where the ultimate source of carbon for a salt marsh food web is, we can use a variety of tools. And one of the ones we use is stable isotopes. Carbon has a atomic weight of 12, and you've probably heard of carbon-14, which is a radioactive isotope. But there's also very small amounts of carbon-13, which is a non-radioactive isotope of carbon. So instead of having 6 protons and 6 neutrons, carbon-13 has 6 protons and 7 neutrons. It's only present in fairly small percentage of the carbon that's out there, but it's enough that we can use it to trace what's happening, because plants photosynthesizing using different techniques discriminate against the heavier isotope to different degrees. So it turns out salt marsh grasses have a number. We use a notation called the Dell notation of around -13, whereas trees are -28 and algae are -22. So we can look at the different animals in the food web, measure their stable isotope composition, and determine the food web. When we do that, we see that going from grass to microbes to small amphipods and then small fish, once we look at a top predator like striped bass, about 45% of that biomass of a 2-year-old fish that's growing up in the marsh came from salt marsh grasses. So it's a very powerful tool, and it can give us some real insights into how the food web is functioning. So this food web support is one of the big ecosystem services of salt marshes, but there's certainly others. One I think many of you have probably heard about is carbon capture. On a per meter square basis, salt marshes and mangroves store more carbon than almost any other ecosystems, on the range of 50 to 250 grams per meter squared per year. And on the right here, you see 2 students looking at a piece of peat that is eroded away, and you can see meters of carbon stored in this salt marsh. So many of the salt marshes that in our area have peat layers that are anywhere from 1 to 6 meters deep. And that represents a tremendous store of carbon. Another ecosystem service is they help keep coastal waters cleaner. The nutrients come into these salt marsh systems. The grasses take up these nutrients. Some percentage of that is then remineralized and again transformed by microbes into nitrate and then into nitrogen gas. And you don't need to worry about the details of the chemistry, but the important thing is by sort of taking this nitrogen, holding on to it a while and allowing the microbes to process it, it can remove a lot of the nitrogen that otherwise would enter the open waters, which are much more subject to eutrophication. Finally, coastal wetlands have an important function as storm buffers. About 2% of the world's land area is along the coast, but it supports more than 10% of the world's population. And these are areas that are very much at risk. It turns out that salt marshes and mangroves do a tremendous job protecting these coastal areas from these storms. As little as 7 meters of a fringing marshland can reduce wave energy by as much as 67%. There's been estimates that if the wetlands around Louisiana in the United States had been intact, the devastation of one of our biggest hurricanes, Hurricane Katrina, might have been considerably less, with less lives lost. So what's the future going to bring? I think you've all seen graphs like this. If we look back in the historical records, sea level was rising at probably on the order of 1 millimeter a year through the 1800s, maybe 2 millimeters a year in the 1900s. And now projections are that we might have sea level rising by more than 1 meter by the end of the century. But these projections are very uncertain, and I'm going to talk about the reason why they're so uncertain and what we know about what might happen in the future. So there's 2 causes of global sea level rise. This is sea level that is rising everywhere. One is that as the planet gets warmer, water simply expands. So the thermal expansion of the oceans is making sea level rise. And the other is that any water that is on land, which flows into the ocean, also adds to sea level rise. Now, the Arctic, which is floating on the water, does not influence sea level rise, but land-based glaciers Antarctica, and the Greenland ice sheets in particular are very important. So early on, about 2000, 2005, the influence of thermal expansion and meltwater were about equal. But now we're seeing that these melting land-based glaciers and ice sheets are having increasing importance. So if you look at the bottom left there, it's a little hard to see, but you can see sort of an acceleration of around 2000 to 2005 of the loss of these ice sheets. So now we're seeing more and more of sea level rise being contributed to by the loss of land-based ice. Now, there are other causes of sea level rise that are more regional. Obviously, if you're in an area where the land is subsiding, that will influence your local sea level rise. There's also areas where the land is experiencing uplift. And there's areas like the East Coast of the United States where currents influence sea level rise. So this big white river that you see in the Atlantic Ocean is the Gulf Stream. It's a very major current that carries warm water north to Europe. And it's so powerful a current that it actually sucks water away from our coast a little bit. So one of the things that's influencing sea level in the area where I work is the Gulf Stream is slowing down a little bit, and that is allowing sea level to rise faster where I'm working. So the question is, why is there so much uncertainty on how much it will rise? Why are we seeing, I showed you some things that suggested maybe we'd have 1.5 meters by 2100. There's other projections that are even more extreme that say it could be as much as 2.5 meters. So why do we have so much uncertainty in these projections? Well, it's not necessarily just a scientific uncertainty in the physical processes. We know as the Earth warms, we can calculate the thermal expansion pretty accurately. Problem is the people. We don't really know what the people are going to do. So on the left-hand, far left, you see different scenarios for potential emissions of carbon over the next century. So the lowest one is the green one there, and that assumes that emissions will slow down beginning almost immediately now and reach zero by 2080. So that's our green projection of the CO2 concentration in the atmosphere, which you see on the right, peaks out a little bit over 400 parts per million. On the other hand, if you look at the blue projection, that's called business as usual. That's saying that there's going to be a continued increase in emissions to at least 2060 and then a leveling off. So we'll put much more carbon dioxide in the atmosphere, and that will lead to a carbon dioxide concentration of 900 parts per million, which is more than double what it is now. So these are projections based upon people's preferences and economics that are a little bit more difficult to pin down. So this is where the huge uncertainty comes from. But the good news is that it also shows that these really high projections can totally be avoided by but by controlling carbon dioxide. So if emission reduction is taken very seriously, some of these worst projections won't come to pass. There are other scientific difficulties, though. It is very hard to really model how fast we're losing this land-based ice. We're finding now that processes like meltwater getting under the glaciers and really accelerating their movement are more important than we thought. So ice loss is a little bit harder to predict than thermal expansion, but not nearly as uncertain as the emission pathway that we humans are going to take. So what does this all mean for coastal salt marshes? And I can add coastal mangroves. Well, as I said, these marshes exist in a very narrow tidal range. Where I work, we have about a 3-meter tide from the very lowest to the very highest. And as I said, the grasses are in a very narrow part of that elevation. They like to be flooded once a day or a couple times a month. They can't be continuously submerged and they can't be continuously dry. So now sea level is rising. What are they going to do? Well, we can look back in the geologic record to see whether they're going to tolerate sea level rise. If we look back in the geologic record, we find no marshes during the period of most rapid sea level rise. So when sea levels were rising more than a centimeter a year, there are no salt marshes. But once sea level rise slowed down to about 3 millimeters a year, we start finding salt marshes in the geologic record. So salt marshes geologically are very young, only 3,000 to 8,000 years old. But that's to get established. Maybe they have a little bit more scope to tolerate sea level rise once they're established. But it is very important to look at that centimeter a year number and think about maybe that does represent some type of barrier. So then the question is, how do marshes keep up with sea level rise? And we're going to just briefly talk about 3 mechanisms. The first is they migrate back to higher ground. They accumulate inorganic and organic material from the incoming tide, and they produce organic matter in the soils, and some fraction doesn't decompose. Well, the migration is simple to understand. On the right-hand side there's a photo of as sea level is rising, the marsh is migrating back into a coastal forest. You can see in the insert all the dead trees with the Spartina growing among them. So if the slope is gradual and there's not too much else going on, the marsh will slowly move backwards. And marshes have been doing that and mangroves for the last several thousand years. But with increased development, as you see on the bottom, coastal armoring, what the marsh might have to migrate to might not be available. So obviously a marsh, you can see on the bottom there, that marsh is not going to migrate past that concrete barrier. Second way marshes keep up with sea level rise is they trap sediment. This is a positive feedback. The healthier the marsh, the more the vegetation, the denser the grass, the more they slow down the incoming tide, and the more the clays and organic matter in the incoming tide get deposited on the marsh surface. So the marsh grasses themselves play a very important role in this. They keep the sediments from being lost. And also the stems themselves are a little bit waxy, so they actually trap the sediment that way as well. So sediment trapping is really important. The other thing is marshes produce a lot of organic matter below ground. For most marsh plants, there is more. If you see a marsh plant that has 700 grams biomass above ground, it might have 1,400 grams below ground. So on the left, you see a core with some pictures of little white roots down there in the bottom of the mud. And then on the right-hand side, you see a CAT scan image of that same piece of mud. And what you see is all those orange and yellow roots and rhizomes. Rhizomes are underground stems that are holding the peat together and producing all this organic matter below ground. The rhizomes especially have lignin in them and don't necessarily decompose very well or very completely. So this helps the marsh keep up with sea level rise by putting material into the sediments. And it's estimated that the maximum that could do is about 3 millimeters a year, but that's a very substantial amount. So this little cartoon sort of summarizes what happens. The tide comes up, the tide goes down. The vegetation traps material and deposits it on the surface. They die, they put biomass into the sediment, and those two factors lead to increase in marsh sedimentation and marsh elevation, which helps keep up with sea level rise. So we've been trying to figure out what is going on now and what might happen in the future. So we're looking at carbon sequestration rates and sediment accumulation using a variety of techniques. We look at long-term sediment accumulation rates, and we look at how much carbon is in them using radiometric dating. We use both lead-210 and cesium. On the far right, you see the activity of cesium in a salt marsh core. Cesium was produced by bomb testing, and that had a maximum emission in the 1960s. So you see that peak of cesium, and we can date that as a 1-point measure as 1963. On the other hand, lead-210, we can date continuously and try to see if the sedimentation rate was linear or has changed over time. And then we can measure the carbon in the sediment and add that all up and say how much carbon has been buried. So that gives us a long-term understanding of accretion rates and carbon burial, but doesn't tell us how things are changing now. To get a much shorter term measure, we use something called a sediment elevation table. This was invented by Don Cahoon of USGS. And what you do is you put a long rod into the sediment and you pound it in till it won't go any further. And then we have this rotating arm that goes on that. And very carefully, in areas where we don't allow people to walk, we take little tiny rods and gently touch them to the sediment and measure what the elevation of the marsh is. And in that arm, you can't necessarily see it, but it rotates around. So for every site, we get about 60 measurements of the height. And we look to see how that changes annually. So we've been doing that in the salt marsh. And what we find is if we look at the accretion rate in Spartina alterniflora, that's the top bulb. So that's the low marsh plants. And then we go down to the far right. Those are the plants growing in the high marsh. It looks like they're keeping up with about the 100-year sea level rise rate of about 2.5, 2.8 millimeters per year. Some of the sites don't necessarily quite do that in the high marsh, but certainly all the others do. Now, if we look at the contemporary rate over the last 30 years of sea level rise, we see most of the high marsh is not keeping up with sea level rise, whereas we do see the Spartina alterniflora continuing to keep up with sea level rise. Another way we look at how much material is being produced below ground and how much carbon is being stored is to use something called eddy covariance measurements. This is a fairly new technique where we can instantaneously measure whether the marsh is taking up or losing carbon dioxide. The picture on the left shows you a picture of one of our towers. And what happens here is there's a device on the tower that measures the wind velocity in all three directions, vertical and horizontal. And in the middle of that little thing that looks like a claw, which is measuring the wind, we have, we have a carbon dioxide monitor. So the theory is that as we're measuring air coming down, we look at the carbon dioxide concentration, and then these are little eddies swirling around all the time. So the air goes down, the air goes up on very, very short time scales. And if the air coming down has more carbon dioxide than the air going up, we know the ground took up carbon dioxide, photosynthesis. And if it goes the other direction, we know the ground is losing carbon dioxide. So the next figure I'm going to show you is sort of shows how we have to integrate these measurements, which are made at 10 times a second over an annual cycle. So we look at the cumulative flux, and we start in January. We see in our temperate areas, the grass is all dead in January. The soil is just respiring. The microbes are active, but the plants are not. So we lose carbon dioxide on net fairly continuously till almost the end of May. Then the grasses are all greening up and photosynthesis begins to dominate over respiration. So GPP is gross primary production, R is respiration. And now those grasses completely reverse everything, and they take up carbon and take up carbon till the end of October, September, where now they've taken up a net of 250 grams carbon per meter squared. And then we lose a little bit more of that over the fall once the grasses senesce. So what we do is do that over an annual cycle and say, what is the net impact of the salt marsh on the carbon cycle? And we also compare the high marsh to the low marsh, because remember, based on the SET measurements, it looked like the low marsh was doing better than the high marsh. So is that due to the action of the grasses, or is that due to sedimentation? These are the same kind of plots. I've only put the growing season parts on there just to make the difference between the sites a little more obvious. But the darker green represents the low marsh, that salt marsh, Spartina alterniflora, and the lighter green represents the high marsh. You can see that in 3 out of the 5 years we've made measurements, the high marsh is less productive than the low marsh. 2 of the years we had a drought and they were fairly similar. But this might be one reason why those high marsh sites don't seem to be accumulating sediment nearly as fast as the low marsh. Now, obviously, what we want to do is take these measurements and try to get a better understanding of all the mechanisms that are involved, and then try to model this out into the future. So what will change if things get warmer, if things get drier? Will these grasses continue to store this much carbon? Will they be able to at least try to keep up with sea level rise? We're also comparing these different areas of high marsh and low marsh for their ability to trap sediments. These might not get anyone to apply here for graduate school. These are students that are out in the marsh during a complete tidal cycle, going from the very lowest tide on the left there, when there's just a little rivulet of water coming out of the marsh, to high tide, which is about 3 meters. And they make measurements every 10 minutes of the current velocity and the water concentration. And we look to see how much nutrients, how much carbon, and how much sediment is retained. And what they find is, again, the low marsh seems to be winning here. The low marsh is importing much more sediment than the high marsh area. So that's another advantage for the low marsh to keep up with sea level rise. So from our work at Plum Island, the conclusion is that even with current rates of sea level rise of about 4 millimeters a year, we're going to see a pretty drastic transition. We're going to go from something that was really dominated by this salt marsh hay in the high marsh that's dry most of the time, to much more Spartina alterniflora, which is flooded almost every tide. And other measurements of erosion are suggesting that maybe we'll have more open water as well. The timescale this is going to happen is going to depend upon sea level rise. And we don't know if the marsh can survive these very extreme conditions. If we went to 10 millimeters a year, for example, we don't know that the low marsh will continue to keep up. But at least for Plum Island, the next century looks pretty good. At least we will have a significant amount of marsh area there, with some change in habitat value, more value to fish, maybe a little bit less to birds. So in the time remaining, I want to just quickly flip over and talk a little bit about mangroves and Spartina alterniflora. And I have not worked on these systems myself, but I have a good colleague that gave me some information. I have worked in mangroves in Panama, and I can tell you that mangroves provide all the same ecosystem services as salt marsh. Carbon sequestration rates maybe even a little bit higher. The storm buffering is a little bit stronger, a very high importance to fisheries. I think the one difference is once they become flooded from sea level rise, there will be a rapid loss of elevation because there are more labile below ground carbon stores evidently in mangroves. But my friend Jim Morris has done some work in China, and he's sent me a few references. And this is an example of Spartina alterniflora expanding into mangrove areas. Now, we love Spartina alterniflora. It's our foundational plant on the Atlantic coast, but on the Pacific coast, it's turning out to be a very strong invader. So what you see on the left is the amount of Spartina alterniflora that was in the system in 95. The blue is 2005, and then the green is 2015. So a tremendous expansion of Spartina alterniflora into this estuary just over the last 20 years. This is sort of what it looks like. You can see there's a mangrove area there, and in front of it, you see this large area of Spartina alterniflora. You also see some fish ponds in the back and in the front, which have been encroached on the mangroves in the other direction. There's been a number of studies on these. If you're interested in this, much good work is being done along the south coast of China. This is a paper that was looking at the invasion of Spartina alterniflora and how to control it. Again, what they found was a very fast expansion of Spartina into this estuary. So the one thing I will say is that most of these studies have shown the Spartina is expanding into these areas, but most of the expansion is taking place on mudflats. So they're not able to displace the mangroves very effectively. What they're really doing is replacing mudflat habitat with Spartina alterniflora habitat. Some ways that's good. It's added storm buffering, but it has some important consequences for the food web, especially if those mudflat areas were rich shellfishing areas. So I know it's a real issue. I think it's, if you are a graduate student out there and you're sort of interested in these questions of sea level rise and what the future of coastal ecosystems is going to be, this question of the invading Spartina versus the native mangroves, what are going to be the loss of ecosystem services and what might be new ecosystem services that could be exploited is really a very good question. So I think right now what we have is sort of a good news, bad news story. The Spartina is expanding and it might provide additional storm protection and habitat, but it might be taking over areas used for shell fishing, and it might eventually even take over some of the mangroves. I think we just really don't know that at the moment. So sort of summarize, salt marshes and mangroves lie at this terrestrial ocean boundary, and they just provide a wealth of ecosystem services that I think we're only now really starting to appreciate as we have seeing these systems under threat. I didn't talk about some of the other habitat values such as recreation, but that's very important where I am. Water quality, migratory shorebirds, and surrounding marshes are often tidal creeks that are very rich commercial fisheries. So I just want to end by saying I've shown you an awful lot of data here. And there's very few of those data points I have taken myself. It really takes a village to do this kind of ecosystems level research. We have many collaborators from institutions all over the United States and even internationally. And I also have a crew of just fantastic research assistants that we've been working with over the years that go out there and do all the hard work. And sometimes, as I was out there yesterday, it's just a beautiful day and there's no bugs and it's 20 degrees C and the sun is shining. But sometimes it's freezing cold or the bugs are biting. So want to just give an acknowledgement to all the people that do the work. So I think with that, I'll stop sharing my screen and let Mark take it over if he wants to moderate.
Great, Dr. Giblin, thank you so much. I'm sure our audience really appreciates your insights into this area. And the one thing that strikes me about sea level rise, just like looking at it as a casual observer, is we always focus on, the ice sheets and the glaciers melting. We're not focused on the science around the impact of sea level change. Is there anything that can be done to help more people know about the impact of sea level rise, not just the dramatic pictures that we see on the television?
Well, I think, unfortunately, at least on the East Coast of the United States, they're starting to see it firsthand. But it's complicated because there's mean sea level rise, but there's also storm surges and there's also changes in tidal amplitude. So there are some natural cycles in both the tidal amplitude. So the tidal amplitude increases and then decreases over a 20-year cycle. So I think depending upon where we are in that cycle, sometimes the mean sea level change gets masked a little bit. So I think people don't always appreciate that. And then it sounds like 7 centimeters isn't that much, but 7 centimeters for these coastal ecosystems is actually a lot.
We did have a question. You mentioned storm surges and maybe implying runoff. One of the questions we had from the audience was related to the salinity of the ocean and from these increased infusions of fresh water from runoff, and whether that's impacting these coastal ecosystems.
The change in salinity of the open ocean is not, it's very, very small, and it has no real effect on the organisms themselves. What it does do is the increased fresh water coming in from Greenland and to some extent from melting of the Arctic ice sheet does influence the circulation of the ocean. So it's more an influence on the circulation than it is on the salinity itself.
I see. And we had a couple questions because Asia's, well known for fish farming and shrimp farming along the coasts. Are you connecting any of the research that you're doing with the impact on fisheries?
So we do look at fisheries in our area. So there's two major fisheries in our area. One is shellfishing, clam flats. And there's a lot of interest in how having the marshes there, even though the clams themselves don't live in the marshes, how much of the clams nutrition comes from salt marsh versus how much comes from phytoplankton in the water. And that's another way we use those stable isotopes. And then the food web support for things like striped bass. So we look at that largely through stable isotopes. There's also increased interest in our area about now maybe using artificial oyster reefs to help protect shorelines.
One of the things that strikes me from this presentation, despite the fact that Ecosystem Center has been around for 40 years, is just the question of like the maturity of the science in this area. Can you speak to that and talk about, whether you're getting enough government support, whether there are enough scientists around the world that are working on this particular issue, and how we can accelerate our understanding and take those findings and piece them together into solutions?
Well, if I said we had enough funding, I would be a very unusual scientist. I think funding is an issue. It's especially an issue where we are, because in the United States, there's a part of the National Science Foundation that funds terrestrial work. There's part that funds the ocean, and there's not that much, there's not a specific, what we call a directorate for this sort of intertidal estuarine area. So sometimes you get funding from one place and not the other. The long-term ecological research sites were set up to try to help address that. But it's a difficult area to work, and it's, I think we're only now starting to get some of the tools that I think we really need to answer some of these questions. Very simple example is that you want to know how much carbon or how much nutrients are going in and out of a salt marsh creek. You have to know how much water goes in or out. But until fairly recently, the really big oceanographic instruments that measure currents just don't work in those kind of systems. And there weren't a lot of tools or people interested in learning how to do that. That has changed now, but just simple things like measuring the water flow over a tidal cycle can be hard. So I think we certainly need some clever minds to think of some new approaches and some new innovative measuring tools starting to come along. But
are you seeing new innovations in this particular area, whether they're with for-profit companies or not-for-profit companies, and those which might be, developing new technologies for metering some of these to make collecting the data easier for the scientists?
I'm seeing some. I think there's been some big improvements in sort of monitoring dissolved organic matter in the water. For example, there's some new fluorometric techniques that make that much easier. It's not a direct one-for-one, but we can calibrate it. I think there's increasingly techniques that can be used to monitor nutrients. At the moment, they're not quite sensitive enough to do the low-level nutrients that we have, and they're affected by salinity. So that's the other problem. You have a system where the salinity, high tide to low tide, changes by 20 parts per thousand. Some of these instruments aren't as effective, but I think we're getting there. I'm seeing some nice innovation.
Great to hear. We do have many people who seem to be experts in this area, maybe students in this area. I know we have some professors from other universities in Asia. So I'm going to throw a question out there that is more technical. So tell me whether or not it's appropriate for you to answer. But the question is, if sea level continues to rise, will it impact the thermohaline circulation?
So that sort of gets back to the original question. The sea level rise itself, just rising the level, I don't think will impact the thermohaline circulation, but the change in the distribution of fresh water does influence that. So North Atlantic deep water is formed sort of in the northern, as it sounds, part of the Atlantic Ocean. And that's very cold, salty water coming from the Arctic Ocean. It sinks, and then that actually helps drive that whole current that ends up coming back in the Gulf Stream 1,000 years later. If the Arctic Ocean gets less salty and that ocean water doesn't sink as quickly, that will affect deep ocean circulation. And that's kind of one of the scary parts about, global change is this. Changing the thermohaline circulation would be a really big deal. Changes the ventilation rate of the entire ocean.
Thank you. Another question that looks like it comes in from possibly a student is, can we use the peat layer as a sea level indicator to establish sea level indices?
Can we use the peat layer?
Yes.
Well, we do, but we have to date that first. So for example, if we go down to the depth of the peat, where the peat hits the sand, that tells us when the salt marsh is established. To get to that, we can't use lead-210, we have to use carbon-14. But if we date that peat layer, we can say the marsh started 3,000 years ago. And then we can get an idea of how much accumulation there was over that time. So that's sort of how that big curve that I showed, that showed how sea level changed over geologic time. That's basically how one of the ways that curve was generated.
I see. To me, this looks like really difficult science. And when I say difficult, it means like, you could go into so many different directions to try to gather data and understand what's going on in these coastal systems. Are governments, creating any policies? Are there, you get funding from a couple of different government sources. Do they have policies that direct the science in a way that's addressing the most urgent issues in the near term?
I think there is a pretty good mix. So in the US, we have the National Science Foundation, which funds large collaborative projects like ours. They're aimed sort of at more basic understanding. They also have organizations like USGS that are sometimes tasked with more specific data collection, which is not to say they don't do basic science, because they do some excellent basic science. But and then we have other groups like NOAA, for example, that set up the tide gauge stations all over the country that measure the rate of sea level rise. So I think we have a pretty good mix of academia and government agencies. It's just there's a lot to do, and we'd always certainly like more funding. We're competing with other things, but and then there's groups that are really focused much more just on infrastructure protection, and sometimes we find ourselves not always working together on some of those things, because what protects infrastructure doesn't always help preserve the coastal natural ecosystems. One
of the audience members asked whether sea level rise can impact landlocked countries. Is there, does the system somehow roll up into a landlocked country and impact it?
It can. And the way that can happen is that, depending upon where the landlocked country is and how big its river system is, as sea level rises, it affects river flow as well. I'd have to sort of think about maybe a possible scenario. But just for example, in the city of Boston, in a big storm tide, what floods the city of Boston first is not the seawater, it's backing up the fresh water flowing down to the ocean. So by changing that freshwater flow, you can impact a landlocked country. And you can also have seawater intrusion, which can affect the aquifer.
Can you speak more to these coastal man-made barriers and what impact they are having, and whether that's the right solution for addressing the sea level
You mean
rise?
think like the oyster reefs type of thing?
No, I'm thinking more of like concrete barricades.
Yeah.
Like that, which be cropping up all over.
Yeah, at least in the Northeast United States where I am, that's been the biggest factor leading to salt marsh loss after sort of direct dredging and filling. But building all these barriers not only affects where the barrier is, but it affects the current flow and the sand migration and everything else. So for example, a lot of marshes are behind coastal barrier beaches. You start changing the sand flow of those barrier beaches, and you start changing the current flow and the ability of those salt marshes behind them to survive storms and things like that. So, you know, as sea level rises, a hard barrier becomes incompatible with marsh migration.
And I suppose that as cities, you know, like Hong Kong and others around the world are, you know, using landfill to extend the land to build large structures, that's also altering these systems. Can you speak to that? Is it the same kind of impact as creating man-made barriers?
I think depending upon how it's done, obviously, if you're covering up salt marshes or mangroves to build high rises, then you are really having a negative impact. But it's possible that these land extension things could also include lower elevations that might extend, which could be colonized, for example. So I think I'm not as familiar with how that is being done.
And, you know, we always ask questions on these 1.5 degree programs of the experts, and our audience members are always constantly asking, what kind of, at the individual level, what sort of choices, decisions, actions do you think people can take to help ease the pressure on rising sea levels in particular in this case?
Well, it all comes down to, aside from just in your immediate area, protecting your coastal ecosystems from damages such as dredging and filling, to controlling the carbon emissions into the atmosphere. And obviously there's things that people can do as individuals, but there's also things they can do to convince the politicians that there is the will to do this. Because I think the real barrier is that there's a lot of things that the world at large, the political world at large, knows what has to be done, but they don't think it will be tolerated. And I think if people let their government officials know, we want this to be a priority, we know it might cost a little money in the short term and it's going to save a lot of money in the long term. So expressing that will to do something is probably almost as important, maybe more important than just making sure you shut off your lights and you put solar panels on your home.
I think that's a really good point. Like people, one of the things that I feel strongly having moved here to Hong Kong from San Francisco, where environmentalism is a social activist kind of endeavor, is that people just need to speak up more and let their governments know how they feel about climate change and about these issues, which is one of the real catalysts for us doing this program. But one of our audience members asked something related to government. Can you please explain whether the conservation of coastal ecosystems is strongly addressed in international environmental conventions and being pushed for by governments? I guess that goes back to a few weeks ago, we had a program hosting one of the lead negotiators for the Paris Agreement. And does the Paris Agreement address any of these issues today?
Yeah, I'd have to say I don't know. I mean, there's certainly been a huge effort to catalog these coastal ecosystems and to measure how much carbon is being stored in them. It's called blue carbon. But I'm actually not aware of whether it's specifically in any of the Paris agreements. In the United States, there is now an official policy of no net wetland loss, but that's with intentional activities. It doesn't prevent wetland loss from unintentional activities.
Mm-hmm. I see. And this may be related to the runoff question, but one person asked whether changes in precipitation affect or influence the salt marshes.
Well, if you'd asked me that 10 years ago, I would have said no, because especially with the low marsh that's flooded almost every day. But at least our eddy flux data sort of suggests that there's a critical period in our latitude. It's somewhere around June to early July, where if we don't get precipitation for 4 or 5 weeks, the marsh grasses seem to suffer a bit. I mean, they're already salt stressed. So if that pore water salinity gets much above 40 parts per thousand, the plants are in trouble. So I'd say it's possible.
We have a lot of people tuning in from around Asia, in particular Southeast Asia. And this is a question from someone in Sri Lanka who said they have a study in the west of Sri Lanka, and they observe salt marsh ecosystems that are heavily grazed. according to your research, what will happen to carbon stock in such places?
I think we did some studies on the high marsh, salt marsh hay, Spartina patens, where it was regularly mowed for use by cattle. And we didn't find any difference in below ground carbon storage or sedimentation. Now, they did it fairly carefully. They only cut the grass once every year or once every other year. But, you know, a lot of grasses are adapted to grazing. So I would say, depending upon how heavily it's grazed and who's grazing it, whether they're ripping up, you know, roots or whether they're just nibbling on the top, might be okay. I'm interested what's grazing them. That they didn't say.
They didn't say. Yeah, so you know, we're coming to the end of the hour here, and I was wondering, Dr. Giblin, if you had any final remarks or comments, or actually any kind of comments you wanted to make about reaching out to other institutions, students, collaborators in the Asia Pacific region that can help accelerate the research in your area.
Well, as I said earlier, I think this question of what Spartina is doing in its non-native environment, what it's doing with mangroves, what it's doing when it's colonizing other areas, is both tremendously interesting and tremendously important. So I think that would be really fun to sort of collaborate on that. And also, what's the genetics look like? I mean, this is a very strange plant. It's polyploidy. Is the invasive form different than what we have here? I think there's just a whole lot of questions. So I welcome people thinking about this and sending me an email or looking for some collaborations.
Perhaps somebody in the chat can put a contact for MBL or your email address. I know we probably have some folks from MBL on the program as well, or somebody on our staff here in Hong Kong can put a contact email address there. But Dr. Giblin, thank you so much for sharing your expertise. This has really been a fascinating and informative program on sea level rise. We really appreciate your joining us from the East Coast.
Thank you very much. It's been a pleasure.
Thank you. For the audience members, we have a brief poll tonight. We're going to do something a little bit different on this program for those on Zoom. So please complete the poll while I tell you a little bit more about the upcoming UN Campus program events. Next week is a holiday in Hong Kong, so our next MBL Oceans mini-series episode will be July 8th at 8 p.m. And next Monday, normally we do our programs on Thursday, but next Monday, June 28th at 8:30 p.m., we'll host Professor Paul Staneland from the University of Chicago's Committee on International Relations in his lecture, Responses to China's Rise in Southern Asia. We already have hundreds of attendees registered for that program, so sign up soon and take your virtual seat in the program. We look forward to seeing you next week. Thanks for joining.